So what we're doing today and what we're starting today is solving these exponential and logarithmic equations. Now, I'm planning on it taking probably 2 days to go through this just because there's a lot of different setups that we can do with solving these. Now, the first one we're looking at is what they call the equivalent property of exponential equations. It's also referred to as the one-to-one property. But with these here, there's a specific way we can solve them. Now, the methods that we'll look at later will still work with these, but just some of them are a little more intricate than others. Some of them work out better than others. Now, the reason we say kind of one-to-one property or the equivalent property of exponential expressions is if b, x, and y are real numbers with b greater than 0, so we don't have negatives, and b is different than 1, then b to the x is equal to b to the y if and only if the exponents are the same, x is equal to y. And what that means for us here is that if I look at this equation, 3 to the 2x minus 6 is equal to 81. If we can write both of these as base 3 to a number, then we can say the exponents are equal. Well, 81 is what? 3 to the 4th. And we could grab a calculator and say 3 times 3 is 9, times 3 is 27, times 3 is 81. So we multiplied 3 times. So 3 to the 4th is indeed 81. And now what we have is this equivalent exponentials or one-to-one property. Because if the bases are the same, then the exponents have to be the same also. That's the only way these two can be the exact same. So really what we're saying is that 2x minus 6 is equal to 4. So at this point here, we just need to solve. And the first thing we can do is add 6 to both sides. These will cancel, telling us that 2x is equal to 10. Divide both sides by 2, telling us x is equal to 5. That's it. And at this point here, if we want to check and make sure that this does work out, we can plug the 5 back in and say 3 to the 2 times 5 minus 6. 3 to the 2 times 5 minus 6 is indeed 81. So it does work out. It is true. Any questions on any of this here so far? Now we can go on and look at problem B, which is the exact same process, except we're going to have to do a little bit more to it to get them to be the same. Now we can look at the right-hand side first. 1/5 to the 3t plus 1. So it'd be nicer if it wasn't as a fraction. And what we can do is move the 5 from the denominator to the numerator. So realistically, we have 1 times 5, but it's the same as 5. And whenever we move a number or a variable from the denominator to the numerator, numerator to denominator, whenever we move it across that fraction bar, we change the exponent from positive to negative or negative to positive. So we moved it up, which took it from positive 1 to negative 1. And the reason we're doing this is now we have a base of 5. Well, 25 is the same as 5 squared. So for this one-to-one property, we're wanting to get the bases to be the same. Now we can apply these exponents. So for this here, we're going to multiply by 2. 2 times 4 is 8. 2 times negative t is negative 2t. The other side, we're going to distribute the negative 1. Negative 1 times 3t is negative 3t. Negative 1 times positive 1 is negative 1. And what that's done is it's given us two bases. The bases of these are both 5. They're the same. So what that means for us is that we can set the exponents equal to each other. So now we can set 8 minus 2t equal to negative 3 minus 1. Negative 3t minus 1. And solve. Well, we can add 3t to both sides. We can also subtract 8. So 8 minus 8 is 0. Negative 2t plus 3t is t. Negative 3t plus 3t is 0. Negative 1 minus 8 is negative 9. And that there would be our final answer. Any questions on any of this here? So really with this here, getting the bases to be the same is what helps us solve these. Now there's going to be methods that we're going to go over later, especially using logarithms, that will also work for these here. It's just here, it's a little bit easier. We have a little less to work with. Any questions on this one-to-one or equivalent exponents? Equivalent property of exponential expressions. You feel good with this here? Yes. Now, one of the other reasons that this does work, and I'll show you this here, is that really at this step here, what we're doing is we're applying log base 5 to both sides. Because our property that we had earlier, log base b of b to the x is equal to x. So here is just 8 minus 2t. So we get these here. Because this and this are 1. So we're left with the exponent. All right. Now this here is really where logarithms comes into play and is very nice. Isolate the, so if we're going to solve this, I'm going to go on with our 4 main steps, or the 4 steps especially the book gives us, is to isolate the exponential expression on one side of the equation. Take a logarithm of the same base on both sides of the equation. Use the power property of logarithms to bring down the exponent, and then solve the resulting equation. So we're doing this really, we could have done this for the last ones, but we can definitely do it for this here. And we want to get the exponents, or isolate the expression, exponential expression on one side, and especially the one that has a variable. Because if we had something like plus 6 to the 4th, I don't need to get it by itself. Because 6 to the 4th is just a number. We could plug that into a calculator, we can simplify it. This entire side right now is just a number. So we really want to isolate any of them that have a variable in the exponent. So 7 to the x. So we got that. Take the logarithm of the same base on both sides of the equation. And what that's saying is here, we have 7 to the x. So I'm going to take the log of both sides with a base of 7. And according to the properties of logarithms, we can move the x out front, which gives us log base 7 of 7 is equal to log base 7 of 60. Well, log base 7 of 7 is 1. So that just simplifies to x. On the other side, we have log base 7 of 60. Now at this point here, there's two ways to calculate this. One is to do the change of base, because that's really saying that this is the same as log of 60 over log of 7, or ln of 60 over ln of 7. So if I wanted to, I can grab the 30xs and say fraction log of 60 over log of 7. And we get this here. We could have done the same thing with ln of 60 over ln of 7. And we still get 2.104. I would go at least, so we'll say 2.104. And that's our answer. Now the other method for plugging it in is in the graphing calculator, because we can go math up to log base 7 of 60. We get the exact same thing, 2.104. And that's it. Questions on any of this here? Okay, yes, that was just the only one. Okay. We want to isolate the exponential by itself. The number that has a variable in the exponent. Well, the first thing we can do is subtract 820 from both sides, because that will give us 10 to the 5 plus 2x is equal to 0, 9, 49 minus, what was that, 820? Yeah. Yep. 48, 780. Yep. Questions on this so far? Now, what do we need to do next? We need to apply log base, what? 10, yes? Of 10 to the 5 plus 2x equals log base 10 of 48,780. At this point here, we can bring the exponent down, 5 plus 2x. Now, log base 10 of 10 is what? 1, yes? So we could rewrite it. We could put this in parentheses and say log base 10 of 10, cancel it out, it's equal to 1. Or we can already simplify it, because we know that's going to simplify down, yes? Now, this one here is nice, because what is the common log's base? Well, the common log's base is 10, yes? Which means over here, I can just say that we're taking log of 48,780. I don't have to put the base. So with log, L-O-G, if the base is 10, we don't have to write it. It's understood. If it's natural logs, the base is understood to be E. We don't have to write it ln of E, ln base E, or log of 10. But now we need to get x by itself. So the next thing we can do is subtract 5 from both sides. Telling us 2x is equal to log of 48,780 minus 5. Well, x is still not by itself. We have to divide both sides by 2, telling us x is equal to log of 48,780 minus 5 divided by 2. And at this point here, we can type the whole thing into the calculator and let it do the work for us. We can say log minus 5 divided by 2. Now, if we go out 3 spaces, tenths, hundredths, thousandths, we have negative 0.1556. That's negative 1.56. Yeah, negative 1.56. And that there's our final answer. Now we could plug this into the calculator. Now, again, if we approximate, we plugged in negative 0.156, it's going to give us something close to the correct answer. It's not going to give us the exact answer because, again, we rounded. We're approximating. Now, one thing that you can use is, let's see here, second, ANS. Now, what that's going to do is it's going to grab the previous answer, as much of it as it can, and plug it in for us. So it's going to be easier than us trying to type the whole thing in. It's going to take it and plug it in for us, which is a little bit nicer. Plus, what was it? It wasn't 880. 820. 49,600. Is that the answer that we started out with? Yes. So it is the correct answer. Questions on this here? All right, there is a part B. 2000. Now again, we want to get E in this case by itself. So the first thing we can do in getting E by itself is 2. Yeah, we are going to want to get T by itself eventually, but at this point, to get T by itself, we need to get E by itself first. Because we could just apply, because again, here we're going to have to apply the ln function. We could apply it at the beginning, but it's going to make it a little more tricky eventually. Because it would say, you don't have to write this down, ln of 2000 is equal to ln of 1800e to the negative 0.4t. We would get this here. But it's going to be a little bit harder to split that up. I mean, not too bad. Because we can say ln of 2000 is equal to ln of 1800 plus ln of e. And we get this here. Well, I can subtract 1800 from both sides. To give us ln of 2000 minus ln of 18,000 equals ln of e to the negative 0.4t. So that does work. Because if we have two things multiplied together inside the log, we can rewrite them as addition. Also, if we have two things being subtracted, two logs being subtracted, we can rewrite it as division. And then this side here, ln of e is 1. So it gives us this here. do we see kind of how that works? I mean, there's a lot of steps to it, and it's using the properties. But over here, we can do this division. We could do it there. This is the same as 1/9. Is 1/9. So I would say at any of the steps from start to finish that require approximating, rounding, do not do those. So if we get something like here 1/9, that's as far as I'm going to take it. I'm not going to put it as 0.1 repeated and at 0.11 or approximate that. I'm going to leave it as a fraction. So if the fractions don't reduce nicely, leave them as fractions. Don't try to approximate at any point. Is equal to e to the negative 0.4 t. Now at this point here, just like the other side, we can apply ln to both sides. And what that'll tell us is that we have ln of 1/9 is equal to, well, ln of e is 1. Really just leaving us with our negative 0.4 t. And lastly, what we need to do is get t finally by itself. So if we want the exact answer for this here, the exact answer is the natural log of 1/9 divided by negative 0.4. Is the exact answer for this here. Now we can plug it into a calculator, say ln of 1/9 over negative 0.4, and get 5.493. So t is approximately 5.493. And that is the final answer. Now, for the most part, not every time, but the most part, especially if we have one ln, one natural log by itself, the numbers that come out of it are not going to be nice numbers because we're dealing with the base of e. E is an irrational number. So the likelihood that e, especially a single natural log, will give us a nice number is not likely, is not high. It's not a likely chance. Questions on any of this here? Hopefully you're noticing a lot of this is more working the equations to get what we want, to get it by itself, than anything else. So looking at this here, there's, again, many different ways to get this, depending on how we want to do this. So I'm going to show you two different ways we can work this. Because looking at this here, there's no real good way to get the exponent by itself, or the variable, or here the numbers with exponents that have variables by themselves, because we have two. Up to this point, we've only had one. So what I'm going to do at this point is apply ln to both sides to begin with. I'm going to apply ln to both sides because I want to use the power property. I want to use the power property. So what that's going to do is move both of these to the front. So I have 2x minus 7. Well, will ln of 4 simplify to 1? No, because the base is not e. Because if it was ln of e, if this was ln of e, then it would. So here we still have ln of 4 is equal to, we'll move the 3x plus 1 times ln of 5. Now the goal of this and what we're doing is trying to get x by itself. If you remember back to inverses, where we had our rational equations, our fractional equations, and we tried to find the inverse, we had to get y by itself. We're doing the exact same process. Now what we're going to have to do next is distribute the ln of 4. So we're doing 2x times ln of 4 minus 7 ln of 4. We have to do the exact same thing to the other side. 3x times ln of 5 is 3x ln of 5. And then 1 times ln of 5 is plus ln of 5. Now at this point here, once we have this set up, we need to get the x's together and we need to get the numbers together. So one of the first things we can do is I can add ln of 7 ln of 4 to both sides. We can also subtract 3x ln of 5. Now on the left-hand side, our negative 7 ln of 4 plus 7 ln of 4 is 0. On the right-hand side, the 3x ln of 5 minus 3x ln of 5 is indeed 0. So what that leaves us with is 2x ln of 4 minus 3x ln of 5. Now at this point here, it'd be very tempting to try to subtract those two. But unfortunately, the natural log of 4 and the natural log of 5 are not the same number. They're not the same thing. So we can't actually add or subtract these. Now, if it had been natural log of 4 and natural log of 4, yes, we can subtract those. Those are the same value. But here, we can't combine those. The same thing is true on the other side. ln of 5 plus 7 ln of 4. Again, those are not the same value, so we can't add them. But ln of 5 is just a number. 7 ln of 4, again, is just a number. Now, are either one of those going to be a nice number? No. So again, even on Alex, it will say to round your answer to the nearest tenth, nearest hundredth. But it will also say do not do any intermediate rounding. And what that means is it doesn't want you to take this here and convert it into its number, what it actually is, and approximate it. It doesn't want you to figure out what this is now and round. Any rounding that you do from the start, once you start the problem to before you find the final answer, is called intermediate rounding, intermediate in between. So we're going to leave it as ln of 5 plus 7 ln of 4. If one of them worked out to be a nice number, if it's for some reason ln of 5 had worked out to be 4, then we could simplify it. Because if we had log base 4 of 4, that simplifies to 1. Okay, we good with how we got to this here? Now on the left-hand side, both of these have something in common. They both have an x, yes? So what we can do is I can factor it out, leaving us with 2 ln of 4 minus 3 ln of 5. And just in case you're wondering, we are almost done. There's one last step. Because now on the left-hand side, we do have x by itself, yes? And we have only one x. And it's being multiplied by our 2 ln of 4 minus 3 ln of 5. Well, all of this here is just a number. So I can divide 2 ln of 4 minus 3 ln of 5 from both sides. And that's our answer. Now that we have x completely by itself, we can approximate. Now that we have x by itself, we can approximate. So we fraction ln of 5 minus 7, that's minus, tried to write that earlier, 7 ln of 4, all over 2 ln of 4 minus 3 ln of 5. 2 ln of 4 minus 3 ln of 5. And that's it. So the answer is negative 5.503. Negative 5.503. This is our answer. Okay, yeah, we're doing good. Any questions on any of this here? I'm going to do this one more time. I want to show you another way to do this. Now, is it easier? Slightly. Because when I first learned how to do these, that's the way I did them. That's the way I did every single one because I like natural log. I liked it a lot better than log base. I don't like how log base works. But here, what we could do is I'm just picking 4. No real reason, I'm just picking 4 over 5. Because I could also do this with log base 5. But if I pick one, I have to use it for both. So I could have applied log base 5 to both sides, or we can apply log base 4. Either one will work. Because the steps are still going to be the same. The first main step, in that we're bringing the exponent out front, is still true, as we did with natural logs. Here we get 2x minus 7 times log base 4 of 4 is equal to 3x plus 1 times log base 4 of 5. Well, if we look on the left-hand side, here we have log base 4 of 4. Well, what is log base 4 of 4? It is 1. So on the left-hand side, I just have 2x minus 7 is equal to, here we still have to do the distributive property, 3x log base 4 of 5 plus log base 4 of 5. Again, we still need to get the x's together and the numbers by themselves. So I can add 7 to both sides. I can also subtract the 3x log base 4 of 5. These will cancel. These will cancel. Well, right over here. 3x log base 4 of 5. Telling us that we have 2x minus 3x log base 4 of 5 is equal to log base 4 of 5 plus 7. We still have to factor the x out, giving us 2 minus 3 log base 4 of 5 is equal to log base 4 of 5 plus 7. Divide both sides by 2 times, or 2 minus 3 log base 4 of 5. These will cancel, giving us x by itself. Log base 4 of 5 plus 7 over 2 minus 3 log base 4 of 5. So in some ways, this makes it a little bit easier because our final answer only has log in 2 different places, and unlike natural log, which was in 4. Now, to make it easier to work with, I would definitely use the graphing calculator because we can go math log base 4 of 5 plus 7 over 2 minus 3 math log base 4 of 5. And we get the exact same answer. Questions on this here? Do y'all like the natural log a little better? It is a lot more steps. There is a lot more logs to it. But for some reason, I like working with ln a little bit better than this log base, especially if it doesn't simplify out nicely, like we had with the previous two, where the one spot x did appear, having log of that base did reduce everything a little bit nicer. Any questions on this here? Now we're about out of time, so instead of starting the next one, I want to look at the previous one again, one more time. 4 to the 2x minus 7. To the 3x plus 1. So we have these two equations here, yes? And again, we're looking for where they cross, where they intersect. And what we can do is say second trace intersection. Now, most likely with how this is set up, there's only going to be one intersection. Part of the reason I know that is both of the exponents are to the first degree. Well, the variables in the exponents are to the first degree. Let me rephrase that. Because in either exponent, we don't have an x squared or an x cubed. We don't have this power. So most likely, there's only going to be one place of intersection. So I could type the two into the graphing calculator and say second trace intersection, and it tells me the x value of the intersection is negative 5.503, which is actually what we found by solving it. So the graphing calculator can do these here and find the intersection for us. And especially for some, when we get a little more complex, and especially if we're dealing with logarithms that have two different bases, we have to do this here because there's no good way, nice way to do it by hand without it getting very complicated very fast. So this here is definitely a good way to find it. And I would say especially, so good way to find it. We're going to finish this to test in here.